All right, so I was able to stretch my spectralizer out and get that button to show up. I'd mentioned about creating the images of the sound. So once I have my display, I check this box at the bottom where it says graph only, and I'm going to select to file. When I do this for the FFT, it asks me to name it. I'll just throw it on my desktop and call it FFT switch. And then I can do the exact same thing on my time series. When I have this where I want it, I'll just say time switch. If it was the real world, I would use an asset tracking number or something like that, so I'd know exactly what the picture represents, okay? But when I have these exported, we can see right here is the FFT. And for the purposes of my software, I can insert this into my problem description, and then the same thing right here on the time series. Those two sit side by side in the software that I use, so I'm able to play the sound, look at these pictures, explain the footprints that I'm looking for, and by the end of that explanation, the customer is able to visualize what the sound really looks like. Does that make sense to everyone? So if you're not using this, I mean, believe me, I'm glad Gary put this in here, because I had about a 12-step process I had to use to crop things out and get it named and all that before. So he made my life a lot easier with this feature. Okay, so any questions on how to create the image? Yes, sir.
Joe, do you attach a sound file?
Absolutely.
Also?
Absolutely. The way our software works is I have an asset. I initiate a problem. I'll document what the problem is and all that stuff, attach the images, and then for each asset, I have a place where I can attach other files, and the WAV file always goes with that problem. Okay? Yes, sir. The question was, with the overlay, what does that really tell me, correct?
Correct.
You know, what value is that? For me, it's two things. Number one, I can say, here's something we know was proved to be a tracking event. And on top of that, I've superimposed with the overlay my recording. So the two things I'm looking for in the FFT are what? Frequency peaks and frequency noise or content in between the harmonic markers. So by utilizing the overlay, I can show the similarities between my recording and a known sample that tells me I have an electrical fault in nature.
Right. What my question is I understand what you're saying there, but on that graph, it doesn't show me the overlay.
Because I didn't pick the right file. That's the only reason why. The type of fault I played was something different than the overlay that I put on.
Do you have one where you can show us the overlay and the arcing as far as?
I'll get one coming up here. Because remember, they're not going to be identical ever. Right. I mean, but the two signatures should exist in the comparison. You know, a couple of 60 hertz peaks.
Right, the 60 hertz peaks should match up somewhere.
No, they won't match. We're just going to have some number of fault frequencies peak on the 60 hertz harmonic. They might be at the end of the spectrum, they might be toward the beginning. There may be one or two on one, and the overlay may have four.
You're talking about similarities.
Similarities, yeah, not identical, exactly. I'm just showing, look, in both of these recordings, they both have some 60 hertz content and a lot of frequency noise. That is an indicator that this fault is electrical in nature. Does that answer the question better? Okay. Any other questions right now? Okay. Let me close this out. Now, the other one we were talking about was arcing. And again, this is, we know, is where it's failing. So we looked at the FFT earlier, and everybody agreed that the FFT for arcing and tracking were similar, right? Both recordings in the FFT for arcing and tracking had what? Some 60 hertz peaks and a lot of frequency noise. One could not God bless you. One could not distinguish the difference between which wave file was which by using just the FFT analyzer, was the point I was alluding to. And to demonstrate that, we'll throw this back on the FFT. And if I turn this off, and I'm going to set that, and I'll play tracking on top of it, I'll show you what I was talking about there. Whoops, not save as. Okay, so in this example here, if we look, both recordings have some 60 hertz where they're hitting in both the arcing and the tracking, right? And both recordings have a very large abundance of frequency noise in between each harmonic marker. Those are the two similarities. So I can communicate to a customer, it is in fact an electrical fault. Does that make sense? But to just look at this tool, there's no way to tell which one is which, agreed? We just know we have electrical faults. So when I go to the time analyzer, what did we say about tracking we're looking for in here? What were the two things that we're looking for in the time analyzer? Yeah, the peaks that change and the changes in time. How frequently is it happening, right? And the more severe it becomes, the more frequently it occurs and more compacted in the view. But the whole thing is, the timing is not going to be uniform when the discharges are taking place. Arcing is a little bit different. If I play the arcing wave file here, we have a totally different time spectrum. Now, if I was to characterize that based on what I heard, what would I say? Well, I've got these really intense discharges that are taking place, but then there's times where it's totally silent, right? So I can visualize that on a time and amplitude base. If I look at the entire view, all 6 seconds, we can clearly illustrate, rescale that so I'm not chopping waveforms here. There we go. We can communicate or visualize, here's where it's quiet, and here's where it discharges. It's quiet here, and then we have a longer discharge, then more frequent discharges out here, then another period of silence, and that large, prolonged discharge at the end of the event. This view is dramatically different than what the tracking looked like, agreed? So the two side by side, you can tell a customer or your supervisor two things. It's definitely electrical, and this is the type of fault that I have, how bad it is, and how frequently it's occurring. Does that make sense to everyone? So you got to use both these tools, there's no doubt about it. The next one is like mechanical issues. Anybody get into those? You know, you have something vibrating. I think the paper I did last year, we found a fault in a 5-year-old square D transformer. The lamination separated because of a manufacturing defect, and what was happening was they're sitting in the magnetic field vibrating. Well, vibration is going to generate heat. We did see some thermal evidence, but it was not going to be found per se without the use of the ultra probe. Now, a certain manufacturer didn't like us too much after that. I won't say it was square D, but well, the funny thing was, I think I mentioned in the paper last year, we had a conference call with square D, and they were like, well, what's ultrasonic testing? Is that like partial discharge? I'm like, you're an engineer and you don't know this? I'm a stupid electrician and I'm going to sit here and educate you? But anyway, mechanical faults are typically a lot different in the frequency spectrum. And if we go back to this one, let me see if it's on, which one was it? Is it this one? No. What's a key thing I talked about last year that will tell you if you have a mechanical fault? What are we really looking for? Well, let me play this, and then we'll talk about it. Peter, does that sound familiar? This one ain't yours. All right, so this spectrum here, first of all, is from the United Kingdom. So what operating frequency, Peter? 50, not 60. All right, what was the tonal quality of that recording? What could you say about the tonal quality? Continuous. Just, we'll say it hums because it don't know the words. How about that? I mean, transformers make noise. They emit ultrasound. That's a normal byproduct of the way it operates. So this is a case where you got to distinguish what should be there versus what shouldn't. Now, a lot of times the flag's raised, well, I hear this buzz. I'll play it again. You can hear not just the hum, but a little bit of buzz in this. And not the kind from the Corona. So you hear that kind of fluctuation in there and buzz? That raised the red flag for the technician, okay? And when he sent it to me to look at, what I did was change this harmonic marker starting frequency, because really nothing's hitting on 50 hertz, is it? Not really good. But when I changed this to 25 hertz, over here to the right, I saw one frequency right here that was hitting. Does everybody see that? Right there. There's a peak right there, agreed? Now, from last year's paper, or maybe the year before, what did I say that a fault frequency like this indicates to you if you're analyzing this? Well, here's what it's not. It is not electrical. Does that make sense? This is a key tip-off right here. If you ever see a harmonic that's half your operating frequency, you can rule out electrical immediately. Because there's no way a 50 hertz system is going to generate a 25 hertz harmonic. But a mechanical issue will. And if you get, it could be any, what kind of mechanical issue? Well, it could be loose hardware. I've seen nameplates with rivets that had loosened up and were vibrating on the case. I've seen shims come out of the windings. The rubber feet go bad. Yes, sir.
Explain that one more time, how you really differentiate between the mechanical and the...
All I said was if I see a frequency peak in the FFT that's 1/2 my operating frequency, I know immediately it's not an electrical fault. And it's because you're not going to see things like arcing, tracking, corona, destructive corona produce or generate a 30 or a 25 hertz harmonic. It's just not going to happen on the electrical side. But on the mechanical side, it will. And it's usually due to vibration, missing hardware. I've seen contact chatter. Anybody know what that is? Contact chatter has produced this, and I've seen it. Missing shims, shock absorbers, and transformers. Some of the dry ones, have this overseas too much, but they'll put rubber feet on them and they've deteriorated. I've seen all these things happen. The laminating separation in the cores will produce these frequencies as well. But for your purposes, if you see this on an analysis, you can rule out electrical. It's going to be something mechanical. Now, that being said, does that mean you won't have an electrical fault eventually? No. Yes, sir.
You mentioned that contact chatter would actually be a mechanical. I understand it's a mechanical moving part. Would that not come into play with your 60 cycles or whatever?
It may or may not. See, usually, if you take a regular contactor, you have a stationary part of the armature and you have a movable part, right? And it closes and the contacts make. If they're sitting there chattering, they're doing what? They're going to be vibrating, number one, but they're also going to be producing arcs. So the vibration of the contacts can result in a 30 hertz harmonic. Does it do that always? No. But I have seen it where just the vibration and the looseness of that, the not making good contact surface, has produced a half frequency. More prevalent in stuff like transformers, but if you see it, you know it's not electrical is all I'm saying.
Well, we did take it when we first was trying out these guns.
Mm-hmm.
And we took it and went around a MCC bucket door, and we found just what you're talking about.
Yep, not surprising.
Could you repeat that, please?
Yeah. Oh, the microphone. I'm sorry. Yeah, if you want to share that. I keep forgetting. Thank you for keeping me honest, Alan.
I was just asking about with a contact, you would think that would have characteristics of the 60 cycles or of the sine wave if you've seen the chatter, and he was talking about the vibration. The contact vibration is what he was picking up. And when we was actually testing the UE against the other equipment, we was able to pick up an example of that by going around the MCC bucket door, and we found a bad contactor chattering with that equipment. So it makes sense now why we did that.
Now, did you look at that wave file recording in the spectralizer?
No, we weren't smart enough at that time.
No, let's characterize differently. You hadn't been enlightened enough at that. How's that?
We'll go with that.
So maybe if you have a recording of that, maybe take a look at it and see if that's what resulted. I mean, if you've already proven that's what the issue, it'd be interesting to see what the spectrum shows. Okay? Yes, sir.
I actually do have recordings. In fact, I got my whole file from the plant.
Oh, okay. He's got the whole file, so maybe after this session here, I'll take a look at it. We'll see if we can find that. So we got the recording here. If anyone's interested, I'll take a look at it afterwards. But Peter right here from London actually had a file when you came across, right? And it was almost identical to what I just played you there. And it's the same thing, only it had a unique production of a frequency when we played it. That sounds similar, doesn't it? Slightly different frequency spectrum, but looking at the 25 hertz way down here, does everybody see that? At the very bottom, but it's still hitting on 25 hertz. Now, I don't have, unless you got an explanation, I don't know why that'd be down below. But it's there, isn't it? It's a 25 hertz harmonic. What does that tell you as the person analyzing that? It's mechanical. It's not electrical. I mean, there could be 10 or 15 things mechanical that it is.
Was this a transformer? Yeah. Did the transformer have a fan?
It was a unit sub. And as a matter of fact, yes, Mark.
I just want to say that another indicator besides the 25 hertz peak is there's lack of frequency contact.
Yeah, that's the other, yeah, I didn't get to that yet. You're right. It looked similar to this. I think it would look like this. No, that's the wrong one. I thought I had a picture of what it would look like, but I guess I don't. It was a unit substation in like a packaging container, just a packaged substation, I used to call them. So it was a self-contained 11 kV primary, 400 secondary? 400 secondary, yeah. And Peter just asked the question about, you know, well, what the heck could this be? And we saw that. But as Mark pointed out, and I'll pull this down, what do you not see in between all the harmonic markers, ladies and gentlemen? No noise at all. Is that a problem? No, I mean, the 25 hertz is we need to find out what that is, but let's say that ain't there. And I see this spectrum. Is that normal for a transformer that's operating under load conditions? Every time. The 50 or 60 cycle hum is going to produce that type of spectrum that lacks the frequency noise. There ain't nothing wrong with that. And, you know, like we were talking earlier, it's very predictable without any faults on it. And you hit all those harmonics because of the stress. It's repeatable. Does that make sense? Okay? Absolutely. Now there's some changes in that amplitude. What could that be? That could be a number of different things, in my opinion. I mean, if it was a contact probe, does pressure on the probe have anything to do with the intensity we might see? I mean, one of the things I learned real early on is if you're going to do trending, you better have the same pressure on the measurement point if you're using the contact. That could play a role. Fluctuations in the load level, you'll see that change it. I mean, we just looked at the file, so I don't know for sure, but those are some things I've seen that can actually change the amplitude.
Do you have any problems with variable frequency drives, harmonics and those or something like that?
Yeah, I mean, the interesting thing about harmonics on the electrical system, the question was about variable speed drives, and do the harmonics produced by drives show up here? I haven't really seen it on this analyzer.
But if it's a dry transformer driven by the variable frequency drive, you better pay attention to the frequency of the variable speed drive to make sure that the harmonics of that, whether it's 42 or 40 or whatever, is what, you know, that's how you make your basis. It's based upon that harmonic, not 60.
That makes sense.
For the switching speeds of the devices, right?
Right.
Yep. And a lot of the local oscillators are at 40 kilohertz, you know, that I've seen or whatever, but yep, no problem. So mechanical, we talk about mechanical, it may be a problem, it may not be a problem. 50 and 60 cycle hum to me is a mechanical issue. It's evidenced by the harmonics being all across the spectrum, but the lack of frequency noise. Does that make sense? All right. Now, that only leaves out corona, right? We've talked about tracking, arcing, this vibration when it comes to mechanical issues. The only thing left is corona. How many folks in here are dealing with systems over 1,000 volts? Just a couple of us, right? So what does corona, and not the beer, really mean? I mean, if you had to define it. It's just an ionization of the air molecules, right? It's a natural thing with the higher voltage levels and the expanding and collapsing magnetic field, it ionizes the air molecules. Is air a good insulator electrically? Yeah, believe it or not, thermally too, if you can keep it still. But can it become conductive? It can if you stress it beyond its insulating point. The problem we have with corona, like we said earlier, is when you have the release of nitrates that mixes with the moisture in the air. Normal, or what I call nuisance corona, you're familiar with the recording from here, sounds like what? How do we characterize the sound? Go away. I mean, what is that sound? Yeah, stir fry, I like that. It sounds like frying eggs, doesn't it? So let me get this rescaled. And when we look at it on a frequency spectrum, where the hell is that? There we go. So let me readjust this. Let's see, 900. And we'll turn the marker on. Make this minus 48. There we go. But the key thing here, notably on the frequency, is what? Everybody knows this if you've been through a level 1 class. So nobody's taken a level 1 class? You see a lot. Matter of fact, almost all these 60 hertz harmonics hit, don't they? Every one of them, because the ionization is taking place at the highest peak of the sine wave. And where that stress is greatest, it's a predictable, in this case, 16 millisecond time base. The FFT produces a nice picture of all those harmonics. The other thing you got is what? All this frequency noise here, right? All that activity. Well, it's an electrical issue, isn't it? Is it bad? When does it become bad? When it becomes bad, right? When it becomes destructive, right? So you get the nitrates released, and then it begins to have tracking imposed on top of that. So I think I have one here that is destructive. Does that sound tonally different? You hear that popping? What did we say popping is associated with? Discharges. So now, this is, I think this is a 4160 volt transformer. There's going to be corona, but you got them pops. That's a key giveaway. What does that look like to you and I? Well, we still have this 60 hertz harmonic, this one, and then look what happens further out. It starts to not hit directly on the 60 hertz harmonic, right? Whereas the corona hit every 60 hertz harmonic. So Mark characterized it as we're masking or losing, dropping off the 60 hertz harmonics out here on the spectrum, but the frequency noise remains. I mean, how many do you have to lose before you say, hey, this is now destructive? You hear the popping and combine it with the losses of 60 hertz harmonics, it's probably destructive at that point. But there's a notable difference even on the frequency display, right? So with corona and the 60 cycle hum and vibration, the FFT actually becomes a more important tool to me than the time domain, whereas when I'm dealing with tracking and arcing, the time domain is really more important to me than the FFT. But either case, both tools need to be used each and every time. Those are really the footprints and signatures of these electrical faults. I mean, I don't want to try and oversimplify it, for lack of better words, but really, if you get accustomed to looking for those types of things, you can be effective using this technology. You can report confidently based on previous experience and known samples by drawing comparisons and looking for those footprints. Does that make sense to everyone? Now, who brought their computer in? We can do a little exercise here for a few minutes if you want. Everybody should have been given a few WAV files. What was the folder name, Mark?
Joe Gerlach's WAV file.
Oh, Joe's WAV files. And inside there should be a bunch of this stuff. So these are things that were sent to me from technicians in our network that, you know, and this is a little departure from what I was doing traditionally, where I'd normally put a presentation together. I want you to play these files and tell me if there's a problem and what it is. It's like practice makes permanent. So for a few minutes here, I think we've got 10 minutes. For those of you who have computers, let's go through a couple of these and see what we can find applying the pointers that I've given over the last hour or so. Does that make sense? So I don't care which ones you pick. Let's take about 10 minutes to go through a few of these, and then we'll pick 2 or 3 of them that you've analyzed to look at as a group. Fair enough? All right, so somebody pick one you'd like to look at as a group that was analyzed. Just shout one out. Which one you want to pick? Anybody. Don't everybody jump in at once. Which one?
Pick one out.
All right, I'll tell you what. Bopat? Okay, this is a good one. This is a good one because I have 2 recordings. So I can do comparisons, right? Now, if I play this in Spectralizer, the first recording, turn off the overlay for a minute. This is off a 34,000 volt switch. You can hear the popping, right? Can you see the popping? You haven't seen it? All right, so maybe we're just not quite set up right. Audibly, there's something wrong with this 34,000 volt switch, isn't there? It should not have them pop. So when I look at the spectrums, 60 hertz here. Let me rewind this a little bit. All right, I'll stop it right there. What does the frequency spectrum tell us? And the way I have this set up right now, my relative scales from -45 to -71, and I'm still out to about 913 hertz on the bottom axis. And this is the view I get with the 60 hertz marker on. What can we see in this view? Some that are on the harmonic, not all of them, right? But we do agree we have some, right? And what else? We got a lot of noise in here. That tells us what? It is electrical, right? Now I'm going to play the second recording on top of this before we jump to the time analyzer and see if there's a tonal and frequency difference. Oh boy. A lot of popping going on there, isn't there? You think it kind of degraded over time? By the way, there was 30 days in between these recordings. So we can hear that. We know the frequency display is different, and interestingly, what did we sort of lose some on the second recording? Some of the noise, right? Which I found interesting. But the real story is going to be where? Well, the time is going to tell us the story. So if we go here to the time series, and I play the first one, we can hear the popping. And I'm going to look at the entire recording in this view, and we can see differences, right? And if I magnify that the way we talked about earlier, just pick a slice in time, we can see the spacing is nowhere near uniform, right? The amplitudes are nowhere near identical across the spectrum. That's a footprint of what? Tracking, because it's a continuous event, right? We don't have periods through this recording where it is completely and totally silent, do we? Through the entire length, we have these discharges. So we know there's no periods of silence. That rules out arcing. But the fact is, when we magnify in and take a slice in time, we can see differences in both the intensity of the discharges and the timing. That, ladies and gentlemen, is tracking. And it was. It was on the insulator on the switch leg. The second one, with all the popping, is even more revealing. I mean, we heard it. And if I look at this as an overall view, oh, I got to get this a little bigger here. There we go. So what I'm doing here is scaling it to full scale, 100 to negative 100 on the bottom here. And what can we tell by looking at that spectrum? There's two things we ought to be able to see here. I'm sorry? Random, still tracking, and increase in intensity. So the fact that these got bigger and certainly more frequent, that tells us what about the severity? It's getting worse. It got worse over time, didn't it? So it's degrading. Is that easy enough to visualize in that fashion? Comparisons are everything in my world. All right, so that was that one. It was a pretty good one to do, right? Let's pick one more here, and I know I'm pressed for time, but let's do let's do this main breaker right here. I actually had a write-up here that the guy sent me. He says, got a customer with a 2,000 amp 480 volt main breaker that has been pegging the dB meter on our contact probe. Oh, really? Well, back your sensitivity down. What did I tell you about dB level? It don't matter to me. It just tells me how close I am to the source of the emission. So he goes on to say it's been measuring it for 2 years, excluded the breaker from the guarantee and recommended testing and replacement. It costs 20 grand to replace. Doing the injection testing doesn't expect it to be effective in determining if it's arcing, tracking, or whatever. Well, I agree. An injection test on a breaker is what? A functional test of the device. It doesn't tell us what really is going on. Does it open when it's supposed to or not? So what he sent me sounded like this. Let's see, turn off the overlay. $2,000 amp main breaker. Say again? Did anybody analyze this one? What about the tonal quality? Should a 2,000 amp low voltage power circuit breaker sound like this? It sure shouldn't. It should be totally silent. And this has been going on for 2 years. What does the frequency spectrum tell us? It's electrical. We have several 60 hertz peaks, and we've got that noise content in here, right? We know it's electrical. If I go to the time analyzer, well, I don't even need to change that view, do I? I can already visualize what's going on just the way it's said here, can't I? I have a continuous event. I have variations in the amplitude of these excursions, and it sure as heck is not the same point in time, is it? What signature is that? That is tracking. So if you can become accustomed to looking for these footprints, you can be confident in your analysis. This tool doesn't lie. It's either going to be electrical or not. It's either going to be a deficiency or it's not. But if you use both of these tools and look for those signatures, you will have a high degree of effectiveness in your program doing this. And I'm not going to lie to you. This takes practice. I mean, it didn't happen overnight for me. I've been doing this crap for 15 years with you guys now, and I still learn. I still consult with Mark and other people to try and learn as much as I can. But as the workshop was called, it's the basics of analyzing electrical issues. So, anybody have any questions? Yes, sir.
Why would you eliminate arcing from this one?
Good question. Because there's not a point in time, if I look at the entire 60-second recording here by double-clicking the stop button, is there any point in that 60-second recording where it goes totally silent? Not one. That rules out arcing. If I begin to see periods of silence in here, then I'm going to know that I have a possible arcing event. Tracking degrades into arcing, so there may be a crossover point, but it's usually well defined in the time analyzer. Okay, good question though. Any other questions?
Other questions?
Well, I'll turn it over to Doug then. I hope you found this useful and a little more interactive. It's a departure from the way we've really done it, but hopefully everybody got something out of it. So Doug?